Hello, everybody, and welcome to today's event on the networking channel. We're going to be having an event today discussing the key takeaways from the recent Dagstuhl Seminar on recent research infrastructures and tools for collaborative network systems research. We are very lucky today to have the organizers of this workshop, who are all world's experts on this topic. We have Georg Carle, who is professor of the Department of Informatics and chair of computer networks and internet at Technical University of Munich. He is highly decorated. He received the IRTF Applied Networking Research Prize, the ACM SIGCOMM Internet Measurement Conference Community Contribution Award, and so on. He has served as the chair of IFIP Working Group on Network and Internet Architecture and vice dean of Faculty of Information and Cognitive Science at the University of Tübingen. We also have Kate Keahey, who is senior computer scientist at Argonne National Laboratory and the Consortium for Advanced Science and Engineering at the University of Chicago. She is principal investigator of the Chameleon Project, which provides an innovative experimentation platform for computer science experiments. Kate is one of the pioneers of infrastructure cloud computing. She created the Nimbus project, which is recognized as the first open source infrastructure as a service implementation. She also co-founded the Software X Journal, publishing software as a scientific instrument. We also have Serge Fdida, who is professor with Sorbonne University. He has had led a highly distinguished career in technical innovation of leadership, serving, for example, as Vice President of European Affairs of University Pierre Marie Curie, Vice President International Development of Sorbonne University, and President of EIT Health France. He is co-founder of Cosmos and recipient of the Atos Renault Chair on Smart Connectivity. He's also the co-founder of the highly successful ACM Conext conference. And we have Henning Schulzrinne, who is Julian Clarence Levy Professor of Mathematical Methods and Computer Science and Professor of Electrical Engineering at Columbia University. He previously served as the Chief Technology Officer for the United States Federal Communication Commission. He was inducted into the Internet Hall of Fame for developing the protocols behind Voice over IP and other multimedia applications. He received the IEEE Internet Award and the ACM SIGCOMM Award for Lifetime Achievement. Before we start, we want to mention that the networking channel is not just one talk, it's a series of talks that happen every 2 weeks. And in 2 weeks, we're going to have an event on how to succeed in early career research, where we're going to have young professors and researchers give their perspectives on how you can get a great start to your post-PhD career in research. And with that, we're going to start the event for today. We're planning to make this a really informal discussion, so we can keep it interactive. You can help us out by asking us questions. The panel would love to hear from you, hear your questions. You can use the Q&A feature at the bottom of your screen. You can also enable closed captions if that is helpful for you to see what is being transcribed in text on your screen, and there's an option to translate our spoken words into other languages there as well. And so we're going to start by turning things over to Serge, who has a few words to say to us.
Thanks a lot, Matt, for the very nice introduction. Just to clarify, Kate will not be able to join us. She is currently traveling, but of course, she has been working with us to prepare those presentations. So I'm very happy to have a short introduction, a very short introduction to the European landscape. Of course, by no means this is meant to be exhaustive. And it is certainly biased by what I believe are the most important points. So this topic of research infrastructures has been hotly debated, certainly started from the early 2000s. And there has been a bunch of initiatives driven by the community and the funding agencies. So in the early 2000s, a good illustration is the Planet Lab facility. And then in the years 2010, the US Genie and the EU FIRE initiatives. And we can say that now we are entering the third generation of what we call mid-scale test platforms. In Europe, again, if we look at this second phase, certainly the umbrella project in Europe has been Fed for Fire. It was a one-stop shop for the federation of different type of testing activities and platforms. And it was funded under the Horizon 2020 program, as you can see, 7 years and basically in the order of 12 million euro. Then we, through the Horizon Europe framework, 2021 to 2027. We have the so-called SNSGU Phase 1, Stream C, which is supposed to support projects related to test infrastructures. And we have 3 projects that are 6G Bricks, 6G XR, 6G Sandbox. I'm not going to present them, but you can look up their website and you will see that the objective is mostly to propose some new technologies, new software components, new demonstrations or test cases related to beyond 5G and 6G. And following this Stream C, there was a second SNSGU phase where the selected project is 6G Sunrise, which is supposed to, again, provide some kind of umbrella for those different type of platforms, adding some new type of services such as camera. And like in the early 2000s, the questions have been quite similar related to what is the value of a testbed, how do you broaden the different type of services, and how you're going to sustain them. But nevertheless, we are now facing some new challenges and issues that I would like maybe to summarize with 3 very simple points. The first one is that it's becoming more and more difficult to provide evidence because those test infrastructures are supposed to equip the research community with capabilities to provide evidence of their research. And this is becoming a little bit scary because, I mean, that's a very interesting, quite old paper, but it states that most published research findings are false. And that the more popular a domain, the higher the likelihood of the research findings to be false. So that's a big, I believe, challenge thrown to our community. Second is that how are we going to cope with the deluge of publications? And at a time where science is driven by data and where we see tons of publication where machine learning and AI is thrown at the problem, it's becoming very difficult to observe whether the publication describes an artifact or whether this is so-called encyclopedical knowledge. And then we still are trying to address the issues related to repeatability. Also, the community since 20 years has been trying to address that problem. Honestly, very little has been achieved in practice. So what it means is that we have to change the narrative. And maybe we have to align our narrative with what you see in this slide. So the 2 pictures here on the left-hand side, you see the square kilometer array. It's a big facility for astronomers that is deployed both in South Africa and in Australia. And on the right-hand side, you see a collider, that's Soleil, for high-energy physics research. So those are research infrastructures, so that the one that we have discussed previously, but they are defined as a scientific instrument. And this is making a big difference. So why this is a big difference? Because it is recognized by the scientific community that over 90% of scientific papers published in the past decade were basically developed involving the use of advanced scientific instruments. That is that some of those instruments basically are considered by those research communities as a reference infrastructure where all the research will be targeting the facility as a means to provide some kind of reference. And that has been demonstrated as a means to accelerate the pace at which the discovery process is advancing, as well as the ability to handle the full research life cycle, so meaning that it also provides some methodology. So how do we target this objective of a scientific instrument? It means that first you have to move or to transition from mid-scale, so which is basically 100 million euro or dollar funding over usually like a 7-year time scale, to large scale, which is the cost of a collider. So a collider basically costs a couple of billion euro or dollars over a 40 years time frame. Fortunately, in Europe, there is an umbrella framework, which is called S3, which is not in Pillar 2, which is the place where all the projects that I have mentioned previously are funded. So those are collaborative projects, usually in the range of a few million euros. But you have to shoot on Pillar 1, where we see this research infrastructure. It's a very competitive call because it happens only once every 4 years, and it is open to all domains. So you have to compete with high energy physics, with social sciences, and so on and so forth. So to make a long story short, we're very happy because this new initiative that I was coordinating, Slices RI, was able to enter the S3 roadmap in 2021. It's very unique because it was the first one in digital sciences. In the past, there were no other research infrastructure to support research in digital sciences. So the way it is organized is that we have a joint investment strategy between 16 EU member states. So actually, we have the political support of 12 member states and the European Commission. What is nice is that now you see that we reach sustainability because as a collider, we basically have a time scale that will provide sustainability until 2040. Of course, the facility will have to be upgraded as, of course, we address new scientific challenges, but that provides the umbrella for sustainability and also the ability to bring a quite broad audience of research communities ranging from networking to IoT to cloud and HPC. So what is new? Of course, we are going to provide access to different types of technologies. We are going to provide access to services. But what is really important here is that there exist under S3 some scientific instruments with no technology. I will say that basically what they provide is access to data. So the research in some other domains is fueled by data. And what is really important for us as well is to provide access, and that's the purpose of Slices, is to provide a repository to open research data in the field that we cover in Slices. And this is very, very important because, as you know, it's not done yet, or it's quite, let's say, disorganized. And it's very important to see how we can provide access to open research data. And we know that there are a lot of hurdles to achieve this, as well as this is of utmost importance if you want to support the full experiment life cycle, and in particular to support reproducibility. So in Slices, we have a metadata registry system. We have a data management infrastructure. I won't go into the detail, but everything is available on the website of Slices, and you can even deploy it. Slices is intent-based. So it means that we understand that the research community has quite a diversity or diverse set of questions to address. But we believe that we cannot provide access to raw resources. We have to provide access to an infrastructure that has been somehow shaped to address some specific research questions. So basically, we challenge research communities, and we have them to come back with what are the most important scientific questions that you would like to address. And then we try to transform them into what we call the blueprint. And we expect the blueprint to become some kind of a reference framework that research community will use in order to provide evidence. So as of today, we have a Beyond 5G blueprint, we have a federated learning blueprint, and we have a Edge Cloud Continuum blueprint, which is about to be available. And again, all those are available on the Slices website. So it's all documented. And I would like to mention here the Slices Academy, because the testbeds are of utmost importance for education and for providing skills to the community. And the Slices Academy is the place where we provide a repository for all those information, hands-on, and so on. So I will stop here. Just want to mention, as it was highlighted by Matt, that in particular, the networking channel is also supported by slices together with the NSF Power and ICM sitcom. Thanks a lot for listening, and I'll be available for questions.
Okay, yeah, that was great. Let's see, I think we can turn things over to Henning next. Henning, would you be able to give us your insights as well?
Let's see if I can go into view mode. Okay, so I'm going to be borrowing on the two expert opinions here of Deep Medi, National Science Foundation, who presented whoops, it's changing automatically. Let me stop that. Okay. Who presented this overview at the Dagstuhl Seminar that frames our discussion today. I wanted to start out maybe by a little bit of a slightly stepping back perspective, namely that while test beds and research infrastructure seems like, oh yeah, we know it when we see it, and systems such as power or slices are obviously in that category, as in their primary objective is to serve as a research platform for other people who conduct research on that, as opposed to being for the benefit of the organizers and funded entities, and was designed for a fairly wide range of experiments in that. The range of research infrastructure, broadly speaking, is much wider. So, for example, many smaller research projects have a component that provides services to others, and that could be as simple as data sets that are usable by other research efforts, or as complex as a specialty piece of hardware that is accessible remotely or accessible by non-members of the research team itself. So research infrastructure really is pretty broad beyond what we'll be primarily focusing on. And indeed, at least in the United States, traditionally, many research projects are evaluated on that are more systems oriented as opposed to more theory oriented, and evaluated on the ability to have what's called broader impact. And broader impact can include the ability for other researchers not directly affiliated with the project to make use of data or specialty hardware or other resources for their own research agenda, as opposed to just purely the research agenda of the original proposers. But from a purely kind of funding perspective, one of the big differentiators is a funding range, Serge was mentioning, varies quite a bit. And all of these are quite useful just to have naturally different life cycles and different objectives. So, like, for example, many universities apply for major research instrumentation, so-called MRI grants. Some of those might be shared resources, but some of those could actually be primarily for local use in that. And in general, and we discussed it at the seminar, one of the challenges that we have is that certain types of infrastructure, and I'll be talking about those briefly in a minute, are easily shared because they're naturally networked. So as in, for example, cloud-style infrastructure and network resources that are controllable by experimenters, those are relatively easy to share, almost independent of the physical location of the researcher that's doing that. But increasingly, say for quantum networks, for RIS type of projects, for some Internet of Things or cyber-physical system type projects, that is much more challenging to do, simply because they interact with the physical world, and we have struggled traditionally to make that available, and not simply because you would need often to rearrange the physical world to make a create a useful experiment. And with that said, let me talk about a few of the efforts. Again, so just for those not familiar with a slide that is useful. So the National Science Foundation has divisions. One of the ones that is most relevant to network researchers is the SCIENCE division, which funds most of computer science, including most networking research within the National Science Foundation. There's obviously also other entities that fund networking related work, not as much as they used to. DARPA, primarily on the security side, and the Department of Energy and high energy physics that often includes networking infrastructure as well. And at the edges of research infrastructure, if you want to call it that, the US has the Internet 2 Consortium, which provides high-end infrastructure which can be useful for experiments as well. For example, they have a Lambda infrastructure where you can get access to wavelengths as opposed to just IP connectivity. So that's not explicitly designed as a research infrastructure, but it is designed to support research both in networking, computer science, as well as physics and other natural sciences. Okay. So what are some of the mid-scale type of infrastructures here? So related to the slices effort is the fabric one, which includes both a network infrastructure shown on the map and on the bottom right, in that the yellow highlights, and includes also the DOE ESNet for high energy physics that are involved as well as cloud infrastructure in that. So these are, and it integrates the supercomputing facilities as well as some other test beds in that. So it could be, in a sense, almost seen as a meta test bed or meta research infrastructure because it provides access to other both commercial as well as like cloud for kind of a classical three big cloud providers, public cloud providers, as well as the NSF research ecosystem like Power that I'll be talking about a bit more. So then we have an edge one called Sage that allows for edge network access to a variety of services for sensing, and primarily because that's what you need edge infrastructure for in that. We have a more more instrument focused one, which has like a X-ray model and microscopy, but is combined with what you might call here, what's called here cyber infrastructure, so data storage and communication as well. So this is a good illustration, and this is probably not a mainstream networking test bed, where test beds that are designed for adjacent disciplines or even disciplines that we don't typically deal with as much, incorporate data processing, networking, analysis functionality, which may well be useful or interesting for networking researchers. And then we've had another type of infrastructure which has existed for many decades, which is not meant for what we tend to think of deploy your new algorithm for congestion control or routing or maybe cloud management or any of these classical networking topics, but is primarily meant to be an observational infrastructure. And again, we've had research efforts all the way from NSF type of efforts that primarily have been supported through Casey's KIDA lab to efforts such as the RIPE Atlas one, which are all test beds, but they're not really meant broadly speaking, to run user experiments of user-created code, but more measure things that are happening in the real world, and not simply because those are less available to others otherwise. And then there's the SEER project. Again, primarily focused on cybersecurity. There's been a long-running, as another kind of branch of research infrastructure that DARPA in particular has funded to provide research infrastructure for people who want to investigate security concerns, from denial of service to traffic analysis to other kind of infrastructure which can be broken essentially, or can be attempted to be broken as part of responsible cybersecurity research in an environment that where you don't have to worry about that you'll harm other real users. In that, then there's increasingly an interest in the integration of networking and AI, as was mentioned in the beginning, namely, how can you create machine learning infrastructure, particularly important for institutions that don't have access to the kind of resources that commercial institutions have, commercial entities do, like Googles and Facebooks and Alibabas of the world, that have access to hundreds and thousands and tens of thousands of GPUs, and that I think is increasingly going to be one where networking is going to play a role, even though the primary emphasis is presumably on the machine learning aspect in that. Closely related to the Slices effort is the Chameleon project, which has been around for quite a while, in a sense that it provides a cloud infrastructure that provide a large number of cores, in that with essentially a opportunity to provide a more controllable version of the public cloud systems using the OpenStack one, so that people who can more readily port cloud-like functionality and experiments there. In particular, that often raises that with the availability of public cloud services, access to computing resources has become more a matter of, can my research budget afford it, versus can I get enough compute resources? With enough money, you can rent as many cores or many VMs as you can reasonably use, leaving kind of high-end AI ML training aside for a moment. But for most computing or more traditional networking one, that is no longer one that is primarily a research budget problem, but accessing bare metal, as in servers that are not just VMs, is increasingly hard to do that. So simply because that's not the objective of the public clouds that are meant to support reliable commercial workloads, not researchers that are trying to try new things that often, by definition, don't work initially. Then I mentioned the Power Project, which is one of the older efforts that consists of 4 different facilities, one of which is located at and near Columbia University. So this is West Harlem, is where Columbia is located, and provides 5G and SDR-based, primarily wireless infrastructure based on the fiber backbone to that. And then the powder effort at the University of Utah, a UAV-based design at UNC, and the University of Iowa, a rural broadband effort that is trying to reach lower density efforts. So these provide complementary research platforms, primarily in the wireless space. And just to illustrate that there are other ones, I'm not going to read through those because primarily because I don't actually know what they do in detail, that smaller efforts are also funded primarily for wireless as well as AI efforts. And here's some examples of smaller funded efforts that illustrate some of the things that I mentioned earlier, namely quantum computing and measurement facilities for terahertz communication, which again are difficult for most labs that are not RF labs to stand up on their own. And then there are some efforts that are at the edge of traditional cloud efforts or traditional research infrastructure efforts, namely to make it easier for research projects to use commercial cloud services. And again, like I mentioned, this is primarily a money problem. And often requires quite a bit of effort just to negotiate with the providers at scale or to try to get educational discounts or whatever. And so cloud buying provides a mechanism to simplify cross clouds or cross the three major cloud providers access for certain researchers. It's not, from my understanding, not a freebie project in the sense that you don't just get free access to AWS or Google Cloud, but if you have certain research grants, you can build that into your grant relatively easily. And that this is a map representation of some of the ones that I talked about, and the power one, the mid-scale infrastructure, and some of the services that are available as well. And that's my quick overview, and I will make the slides available. And obviously, Deep Mehdi at NSF, I would be able to provide more detailed information on any of those more than I'm able to.
Okay, thank you, Henning. That was great. I think next we're going to hear from Georg. Could we hear from you, Georg?
Yes, I will continue. So I will quickly introduce what it means to organize a Dagstuhl seminar, and then which objectives we started with and what we came out with. So the kind of those of you who didn't hear of Dagstuhl should get an impression. It's a castle that was converted into a meeting facility, following some examples of monasteries. Like it's in the middle of nowhere at Western Germany. Usually people may go out for a walk in the green, and apart from that, they are enclosed to not escape the topic, listening to presentations and heatedly debating over the day, and following that in a wine cellar for further discussions. And the format is created following an example of mathematicians who meet in Black Forest since Second World War to establish for computer scientists an environment where you openly discuss ideas, talk about unfinished things, and establish trust and friendship among the scientists. That makes it very different to the typical conference settings. And many people characterize it after having attended a seminar to be that this was the most productive academic event they have experienced. And this is also what I would say. So kind of as organizers, we came up with the impression we should try to organize such a seminar, and there is a competitive setting. You explain why you want to organize a seminar, what are the open challenges in this domain, and what would be the right participants to do this. And then a scientific evaluation committee selects among the proposals those which they consider to create most value for the community. So we kind of assembled a set of experts where we said they are the right mix. Some of them built test beds to be used by others. Others are doing research either on their own local infrastructure or by using testbeds, and are able to express what they hope the testbeds will develop to. And yet other representatives were from funding agencies from the US and Europe. And so here is the full list. You can also go to the Dagstuhl homepage of the seminar where they are all listed. And kind of the goals, this was how we phrased the need for such a seminar, and how we also introduced it to the participants so that they could then help producing good outcomes. So we said, okay, there are examples we could look at from other domains, but these other domains have usually subjects of study that don't change. Like what physicists are interested in is the world outside, which kind of doesn't change, just their methods and infrastructure changes. While in computer science, we're faced with the fact that the questions always change, the systems in which algorithms get executed change. And so already 22 years ago at SICOM, we had a workshop where we said, experimental results, there are a lot of problems. Kind of, it's difficult to reproduce other people's paper. And if you talk to the research group, they may say, oh, these performance figures were produced in a setup by a PhD candidate who already left, and he did some magic at a couple of computers networked together where we wouldn't know ourselves how to reproduce locally. A number of attempts were done to improve the situation. Around a SICOM reproducibility workshop and further discussions at the academic community, the system of badging. So you have artifact evaluation committees and you get reproducibility badges, showed you can do certain things, but at the same time, while this is a progress, there still remain a number of challenges. So these challenges were kind of the starting point. So we said, yes, we need to be able to make reproducibility and artifact evaluation less a burden and more reliable, more predictable, easier to do, easier for those with interesting research to actually go that way. We also say, for experiments, there would be need for some software frameworks that help that experiments are orchestrated in the same way, and that there are tool chains that produce the right outcomes, the right data, also to be accessible by others. And that some people are able to create an experiment that they can share in software by others, who then would be able to kind of modify certain aspects, a concept which we call malleable, where we say the tool chain needs to be enhanced for providing that. And we said also there are a couple of other challenges, like how to care about sustainability or usability of the infrastructure. Also questions about how to best use money from the funding agencies. How many different testbeds do we need? And what would be the characteristics of them? And what commonalities would be good for the different testbeds, and what would be important distinguishing elements? So as part of the seminar, we came up with giving us a schedule, having a number of presentations by the participating experts, then discussing among us what would be the right set of topics for breakout groups, where they have a time slot to come up with their view on the specific topic, and then in a plenary share the outcome and we would discuss about it. And then we also organized a World Cafe around a couple of themes to which we had collected questions over the duration of the seminar. And all participants in rounds added their view on these questions. And these were, again, the outcomes discussed in the plenary and consolidated in a set of final discussions for the conclusions and key recommendations, which I share in the following. And so we started as conclusions, kind of agreeing that it's worthwhile for computer science to make the effort and build important research infrastructures, and that they should, as Serge already had pointed out, evolve to become scientific instruments that are the basis for kind of very solid scientific advance and are able to precisely measure things. And such research infrastructures should give access to all relevant scientists to these specialized advanced resources to be able to execute cutting-edge experiments. So on one level, we said high-level conclusions would be, yes, research infrastructures are a strategic investment, but that the investment becomes a viable investment, it also requires to get the relevant community engagement that starts with educating those groups what you can do with the instrument, help them, make an effort to kind of enhance the knowledge and also share things. And among sharing things, we said, what is here point B, open access to the results and support by tools for easy data sharing is key. And this is along the lines of fair, findable, accessible, interoperable, and reusable principles, together with the related tools. And then we had another high-level conclusion, which was this type of research infrastructures, as they organize or help to organize how research is done, there is a synergistic network effect, kind of as the value of these research infrastructures, if they are properly complementing each other, and if they have tools that can be used in their context that allow to better harmonize how research is done and to exchange things, that helps that kind of the value grows according to a network effect. That is a highly positive outcome. Then we discussed how many research recommendations would we have. Overall, we came up with 12, which I quickly summarize, and I want to point out there are different views about what would be the most important 2, 3, or 4 recommendations of them. And this is maybe also something we can debate in the Q&A following my talk. So we said, yes, of course, there should be clear scientific objectives or scientific questions we want to answer with a specific research infrastructure, like when we propose to build a new one, to answer what? Then, number 2, have everything in place to foster a strong scientific community, like what kind of workshops do we need, what kind of onboarding? Then ensure that FAIR principles are easy to implement and to make the outcomes accessible. Then number 4, do everything that reproducibility is kind of, it's built in by design into the approach. Then number 5, it must be understood it's a multi or many-year investment strategy that is necessary. So the usual project cycle, 2 or 3 years, or 5 years, or 4 to 5 years is not enough. We rather have a strategy that is aligned in like a decade. Then abstractions are needed. for kind of both the software that produces the experiment outcomes and also the evaluation. And finding data and having good access is again what the tools need to support. Number 8, kind of if we have existing infrastructures like a certain testbed, we need evaluation criteria to decide, is this the way to follow and to invest more? Or do we need to change certain aspects of the approach? Then user experience, we said, is key, like how to make it easy for a new experiment to be set up by a scientist who did not yet use a certain testbed. Then the whole tool chain and software framework need to foster interoperability and openness. Then we see this need for flexibility and adaptability of the experiment artifacts so that other scientists can either modify them or compose them to larger systems that are able to be used to answer certain additional questions. Then, as number 12, the sustainable development goals, of course, need to be addressed properly. And these recommendations, the participants, we are still in the progress of finalizing a report. There is a preliminary version for those of you who can't wait for the final one to be published by Dagstuhl, already now accessible. And well, to kind of start the Q&A, I want to come up with my selection or shortlist of recommendations, but as I already had said, there are many different viewpoints about what are the most important ones. So the first one, the multi-year investment strategy, it's not a new insight, but we need to kind of take it serious and come up with how to implement it for the coming years. Then having the tool chain that supports the FAIR principles in an easy-to-use manner. Then optimize user experience for conducting experiments, and having the whole approach done such that by design it's integrated to achieve reproducibility, composability, and this ability to change the software artifact that is used for the experiment, which we call malleability. And with that summary, I would like to finish the presentation, and we're open for questions and comments.
Yeah, thank you. That was very interesting. We can take audience questions now. If anyone has questions, you can use the Q&A feature at the bottom of your screen. We have some audience questions already coming in. I think the first question we wanted to ask the panel was about what sort of interesting takeaways did you have from the event in terms of, what are the most interesting results that you heard there? What are the most interesting findings or options or observations that you heard? Would you all be able to talk a little bit about that?
Serge, you want to go first?
Yes, I can start. They were somehow summarized by Georg, but I can maybe pick up one and then we can continue. I'll be happy to touch base on the second one, but maybe the first one, which is not that surprising, is about the user experience. This is something which we know is quite important because researchers, they are very careful and concerned about the time to learn how to use the facility. And maybe this will translate into the way we have to design the facility itself. And I see there is a question on the needs in the chat that we can address later on. My take on this is that certainly, although researchers would like to have a quite diverse facility because they have to address different types of problems, we have certainly to reduce the type of research question that we have to address to be able to onboard them on the facility to, again, reduce the complexity. So basically to lower the barrier for experimentation. So I think this is something really important. And it has to go with what we try also to achieve through the Slices Academy. So basically providing hands-on to, again, make all those components quite easily to manage and easily accessible. So I think that's a very, very important point. And of course, it comes with others, but I'll take that one first.
Yeah, just to amplify that a little bit, one of the struggles that I think we are facing in networking and systems test bed is the struggle between generality and specificity. So the generality ones are the kind of more cloud-like networks where you have compute storage and networking capabilities. They often then compete both in terms of usability and in terms of just the operation model with commercial cloud operators. Many graduate students are familiar with a cloud service of one sort or another and may have taken a class that includes that. So learning a new interface, a new API may be challenging. And then on the other side, and this has been a bit of a problem, speaking locally for the Cosmos test bed, is anticipating what users need when you propose the test bed is hard. So for example, our test bed at Cosmos started when 5G was all the rage, and that's what we could get hardware for. Now, obviously, there's some movement on to whatever the next generation might be. The other related issue is that when we think of research test beds, we didn't really discuss that as much, but it did come up, is that we really have two audiences, broadly speaking. Namely, one is high committal audience, as in your PhD student that has a whatever 3, 4, 5-year time horizon and needs maybe highly specialized and maybe high performing infrastructure. And then you have researchers that have a lower commitment all the way from a class project in an advanced master's level or senior undergraduate class to somebody who's doing a master's thesis or some other more short-term effort in that, and whose research objective and ability to learn and engage with a new platform are much more limited. So it is a struggle to support both kind of a long-term commitment researcher that is looking for high performance, high specialization, lots of functionality, and somebody who's just trying to do a class research project who has a month to do that effectively and is in a very different situation from a capability versus learning curve type of perspective.
Yeah, and I would like to add kind of one insight I got from the discussions was those operating the testbeds reported there is some marriage effect. Users that once learned how to do something successfully in one testbed apparently get married to it, no matter whether there are other testbeds that might have certain advantages. It rather shapes what they do in the future, and which probably is the outcome that there are so many specifics in the tool chain of the different infrastructures that the price to change from one to the other is high, which possibly can be kind of improved in the future by having more common abstractions used across the different infrastructures.
And I don't and there's a general, not just for marriage, but kind of an intergenerational one, because often what the advisor used when they were a grad student informs what they're comfortable with when they advise the next generation of students. So that probably shapes preferences more than we'd like to admit as kind of being on the other the age side, so we'll say on that. So and that inherently leads to the question of can we provide, given that there is no right single answer, is there a good division where we keep some functionality that may not be the most recent and best, but is familiar, even if it is more limited, that is long-term stable, just like we do for operating system, where you have a version that is kind of, you can count on it to being around. And then there's a bleeding edge version where we just tell people, yep, we're just experimenting, or this is a one-off thing for a resource that is not commonly available. Think like RS type of thing, or UAVs, which are just hard to couch into cloud resource terms, maybe. And those are resources that you should expect a steeper and longer learning curve for, but will also offer in other testbeds maybe things that you can put in a textbook, for example, just to give another stability one is, it's certainly nice if you can prepare course materials of various duration and you have some expectations that students 2, 3, 4 years from now can still conduct those experiments without the instructor having to completely rewrite and re-engineer assignments every year that are more research-oriented.
Okay, thank you. Those are very helpful answers. We have some more questions coming in from the audience. The next one we have for you is about how to do various other forms of research. There's a question around meta research. Is it important to study how to create these infrastructures themselves? Is that itself a research question? There's another kind of related question on are there ways to do research on the ossification of the internet? The internet is hard to change. Are there ways to, are there measurement infrastructures that can help us study deployability of systems and so on? Do any of you have questions around those?
Yeah,
I can take
I'll start. Go ahead.
I take the first one. I hand over the second one to you, Henning. For the first one, my experience on slices with respect to meta research, I will say, is that the other domain science care a lot about the scientific instrument. So we see that they are very careful working all together between those who are basically addressing the research questions and who are in charge of developing the infrastructure. I think this is missing in our field. Also, I fully agree with Terry that we need this meta research. There exist a few workshops and events where this work can be promoted, but this is not similar to what we see in other domains. I used to say that also with respect to the question of Fally Gay about the needs, we don't have the Higgs boson. So it's much more difficult to convince the stakeholders about the need for the infrastructure. But once this is being done, we also have to go back to the research communities because they will be responsible to basically define the research questions and help us to transform those research questions into infrastructures.
And just the hard part, I think there is, we all agree, there's a lot of discussion at a seminar, at a doctoral seminar on even defining metrics as to how you evaluate it, because one of the hard parts for research that we do well when there's an identifiable metric that we can at least compare, given the diversity of test beds, it is challenging to define that in a way that is useful for the next test bed, as in what can we actually learn from that experience, and can we compare different approaches, even though the test bed, the nature of the experiments, the user community, all that may differ quite significantly. So this, I think, remains a unresolved challenge that I don't think we have a good answer for, to do it more than just generational learning, where people pass it on more informally between generations of testbed builders.
Okay, that's great. Let's see, I think we're out of time. We want to thank the panelists very much for their insights and for putting together such a interesting event. We're gonna have a recording of this session put up on YouTube. It's gonna be linked off our main webpage. The audience asked a great number of questions. Very sorry we couldn't get to all of them. We're gonna put them up on the Slack and we're gonna try and answer some of those the Slack after the event. So if you're able to join there, that would be great. And if you're able to join us for our next event, that would be very wonderful. The next event is going to be in 2 weeks, and it's going to be on how to succeed in early career research. So thank you very much.
Thank you. Bye-bye.
Bye-bye.